questions from various. We'll look at some typical questions of various things in relative motion, including the two cases in particular we had discussed last time. Oh, right. And we discussed one other very important thing, which was relative motion between two projectiles, right, last time, or two objects in motion under gravity, where we saw that because both such objects will have the same value of acceleration, the same acceleration vector, so their relative acceleration becomes zero. So looking at the motion of one object relative to another, it just becomes a simple uniform velocity motion. So it's very easy to solve situations like this typically using relative motion. So that's an important application of relative motion. Okay. So as I said, we will start with a new definition related to relative motion today. And you may or may not have heard about this term because I'm not sure this is exactly explained 100% in Resnick Halliday or any reference book for that matter. So this is a term called the relative velocity of approach or separation between two moving objects. So because this is something pretty common that we use in certain applications, so we will give it a special symbol also. Okay. So V approach or V separation. So the definition of this is like that at any given instant, okay, if two particles are moving such that the instantaneous distance between them, okay, is either increasing or decreasing. So if it is decreasing, then we say that they have a approach velocity. If it is increasing, then we say they have a separation velocity. Then the instantaneous rate of change the instantaneous rate of change of this distance is called the approach velocity, which we can abbreviate as V approach, or the separation velocity. So just like familiarize yourself with this definition, and then with examples we'll understand well about this. So this is why I'm saying this is apart from being something very interesting, it's important also, because not only certain types of kinematics problems we'll solve using this, but various constraint relations can be developed using this concept, and it can make life easier for all constraint relation type of problems.
Okay, sir.
Okay, which sometimes become very complicated using calculus otherwise. Yes, Beta.
So this won't apply in the cases, right, where objects are moving in the same direction with same velocity?
In that case, it might become zero. If two objects have identical velocity, then their relative velocity is zero. Okay, if their velocity vectors are identical, both in magnitude and direction, that means there is no relative motion between them. Okay.
Yes, sir.
So that means what is happening? The distance between them is not changing. So yes, it will not apply, or you can just say that the value of V approach or V separation becomes zero in that case. Huh?
Okay, so that's the only case where V approach and V separation will be the same, right?
Yes, that's. I won't say only case. So that's where this becomes interesting. Okay, there is another case also where. Okay, so we'll discuss about it case by case, and you'll understand. Okay.
Yes, sir.
Okay. So now, for example, something rather simple like this, that suppose we have so I'll just take three cases of this example. So two objects A and B. The simplest case of this is if they are moving like this. if they are moving directly towards each other, you can just see that their relative velocity is only their approach velocity. So suppose we have something like this. This is moving at, let's say, 2 meters per second, and this is moving at 3 meters per second. So we can see that if the instantaneous distance between A and B is x, then you can see from the diagram that 2 plus 3, that is 5 meters per second, is equal to the rate at which x is decreasing. And just think of it like a constraint kind of thing. The quantity x is the distance between A and B. So A is coming closer to B by 2, B is coming closer to A by 3. So the relative velocity along this line AB only is 5. So that becomes minus dx by dt. So we will say here that the approach velocity between A and B is 5 meters per second. Okay. So it doesn't matter whether they are accelerating or not. There, what might happen is that at the next instant, these velocities might be changing in either magnitude or direction or both. But it doesn't matter. At this given instant of time, they are both moving in such a way that the quantity x, that is the distance between them, is decreasing at the rate of 5 meters per second. So that means they are approaching each other at 5 meters per second. Okay. Now we can have another situation like this, let's say, where A is, let's say, moving like this at 2 meters per second. And this time, let's say B is moving in the opposite direction. And again, it's moving at 3 meters per second. And this is some instant of time t when we are looking at. So this time we can see that what is happening to x at the given instant. At the given instant, 3 minus 2, that is the relative velocity of B with respect to A, 1 meter per second. It is the rate at which x is increasing. So that means we can see that A and B are having a separation velocity of 1 meter per second. Okay. And this we can also express like this, that they are having an approach velocity of minus 1 meter per second. If I say that some two objects are separating from each other, that means x is increasing with time. So that means the rate at which x should decrease with time, minus dx by dt itself is a negative quantity. So saying that separation is plus 1 is the same thing as saying that approach is minus 1, or saying that approach is plus 5 meters per second in the previous example. It's equivalent to saying that separation velocity is minus 5. But generally we don't do that. If two things, the distance is decreasing, we say they have approach velocity, and two things, the distance is increasing, we say they have a separation velocity. Okay. Now likewise here, suppose we have a situation where they're moving like this. This is moving at, let's say, 3 meters per second, and this is moving, let's say, at 4 meters per second, but opposite to each other and along this line joining them only. So then in this case, we can say that they are outright having a separation velocity, which will be how much?
7
meters per second.
Yeah. So here also you can see that 3 plus 4, again in this case, is acting in such a way that 7 meter per second is an instantaneous rate of increase of x with respect to time. So they are having a separation velocity of 7 meters per second. Okay. So this is the very simple case of approach and separation velocity. And like the case that Janvi you were talking about just now, that if both of them are moving in the same direction with the same speed, like this was 3 instead of 2 in the middle example for A, then the approach or separation velocity would become 0. So that is of course a special case. Okay. But for us now, the more important thing will be the 2-dimensional or 3-dimensional version of this situation. What if A and B are not moving along the line joining them? Okay, then how we deal with it? So we'll come to that. Okay, but you can make a quick note of these 3 situations if you like, or just make sure you understand them.
So in circular motion also, right? If they're both having the same velocity in circular motion, then also their velocity of approach and separation will be the same, 0.
In circular motion, the reason is slightly different. Actually, what happens is the velocities of two objects in the same circle can never be equal, because what is happening now, the velocity vector is along the tangent. You understanding now, beta?
No, sir, not in the same circle. So they're both transcribing two different circles of the same radius with same velocity.
Of course, that will happen. Okay, but even if two objects are in uniform circular motion along the same circle with the same speed, now that's also a very interesting case. Then also what will happen? They'll always describe a chord which is remaining fixed in length. Think of that, like two people running on a circular track at the same speed, but one has got the head start compared to the other. The distance between them will never change, no?
Yes, sir. The angle will remain the same between them.
So that's another case where you'll see that the velocity vectors are not equal because they are different in directions. But there's separation or approach velocity will become zero. Okay, so we'll come to that also. We will discuss. Okay, now let's look at a situation.
So 1 minute, I was copying the last diagram.
Yeah, sure.
Done, sir. Thank you.
Okay. Okay, now see, to understand this concept in a 2 or 3 dimensional situation, now what we'll do is we'll take a situation where one object is still at rest. Okay. And only one object out of the two are moving. So let's say this is at the moment the line joining the two objects is this one. Okay. Now B is at rest, let's say. Okay. But A is moving. And the difference is now A is moving at a velocity which is like this. This is A's velocity as a vector, and this angle is, let's say, alpha. So if the distance between A and B is x now, you can see that here minus dx by dt at that given instant will become the magnitude of VA into cos alpha. Okay. Now the thing is, you have to understand like how I can justify this, whether this makes sense or not. Okay. So let's visualize the situation. Yeah, does it make sense? Yes.
So we will separate it into components, and the sine component will be looking like this vertical motion with gravity G downwards.
Exactly. Okay, so like suppose we draw a coordinate system like this, or even better, we take this as our x-axis like this. Okay, so B is located at the origin and it's fixed. Okay, whereas A's position, now see, A is in general going to move like this now. So in general, if I said that okay, A's position is some x comma y, and this is the x-axis and this is the y-axis, and A's velocity is like this. Okay, at an angle alpha. So at some instantaneous angle, let's say theta. Okay, like this. So then what is happening? The distance between A and B right now, instead of x, it would be s. So s would be root of x square plus y square. So what about ds by dt? It would be rate of change of this whole distance. Okay. Now it would be the rate of change of this distance in such a way that dx by dt, you can see in the above diagram, is minus v cos theta, and dy by dt is equal to plus v sine theta. Right, this is just the components of velocity. I've just expressed the velocity in component form. Nothing very fancy about this, you can understand. If I just write the velocity as in vector form, it is some vx I cap plus vy j cap. And what is that vx? It is the instantaneous rate of change of the x coordinate. It's the instantaneous rate of change of the y coordinate. Okay. Now you can see that at this particular instant, like let's say this is some time t1. So at time t1, what is happening? At that instant, the y coordinate is 0. Okay. And the x coordinate is some x. And VA is some value V. And theta's value is some alpha. So when we substitute that here at this instant, we can see that the instantaneous distance is only x. So ds by dt is equal to dx by dt. Okay. Which is equal to nothing but minus VA cos alpha. But that is happening only at that instant. Understand this? Okay. At a later moment, when even an instant later, even a time dt later, when A is moved away from this x-axis, then the whole situation has changed. But instantaneous means at that moment. No? So at that moment, the rate at which the distance between them is changing becomes minus VA cos alpha. So we will say that A has an approach velocity. Okay. So approach velocity of A towards B is equal to VA cos alpha. And like you were just now saying, another easy way to understand this whole situation is that instead of, this whole derivation which I've shown you over here, you can also think of it like a superposition. Superposition is like a superposition is the term we use in physics when we are looking at two events happening together. Superposition means overlap or together, simultaneity or overlap of two events. So instead of this, if we look at it like this, that the fact that A is moving like this, with a velocity whose magnitude is VA, but whose direction is alpha like this right now. So we can visualize this velocity VA as the superposition of two components, one that is directly towards B and the other which is perpendicular from B. So we can say that it has a component towards B. We can call that as the parallel component of the line AB of VA cos alpha. Okay. And we can see the perpendicular component is VA sin alpha. Now, at the moment, we are interested in how X is changing. We are not interested in how Y is changing because B is lying at an X displacement compared to A. So we can see that minus dx by dt is equal to VA cos alpha. So that's why we can see that the approach velocity is equal to VA cos alpha. Okay. So while the other component is there, but at this particular instant, because it is perpendicular to this line joining AB, it does not make any difference to X. It does not contribute to dx by dt. And at the moment, what is the distance between A and B? It is that X only. So that's why the instantaneous approach velocity is becoming VA cos alpha. Okay. So hope this concept.
So how will you calculate velocity approach or approach by if a string is attached to a wall above it, and we are
Yes,
projecting
I'm coming to that, but step by step. Okay, let's first understand fully the definition of this. Okay. So one of the things you will learn by the end of today's lecture is that thing, that how to get the constraint relation in that kind of situation. String at an angle and a pulley system and all that. How to get that constraint relation using this concept rather than the thread length conservation concept.
Done, sir.
Right. Now, likewise, you can also understand that if on the other hand, what was happening was suppose the object B is moving in this direction, such that this angle is some alpha, and this time the object A is stationary. So now you can see what is happening. They're separating. They're not approaching each other. They're separating. So at this particular instant of time t, the rate at which the distance between AB would be increasing. Okay, you can see would be plus of dx by dt would be equal to v cos alpha in this case. Okay, so we'll say that the separation velocity of B with respect to A is equal to v cos alpha. Okay, and that means, I mean, when we say B with respect to A, it's the same thing as A with respect to B, because if you get in B's frame, A's velocity is like this, backwards like this, so it also has. So now we can generalize this situation further, and we can say that suppose A and B were both in motion in random directions. Okay. And though I'm drawing this diagram in 2D, but it will apply equally in 3D also. Suppose one of them has a component of velocity, one of the components which is actually perpendicular to the plane of the diagram. Even then, this concept that we are applying will hold true. Okay. So यहाँ पे suppose A has a velocity in some random direction like this, and B has a velocity in some random direction like this. Okay. They could have been sort of diverging also, but I've just taken a situation where in this case they are both converging. So this is the instantaneous velocity of A and B at some time t, and they happen to be such that the angle that this instantaneous velocity is making with the x-axis here or with the line AB is alpha, and the angle that this one is making is beta. Okay, so then again you can use superposition. Okay, suppose only A had been moving and B had been stationary. Okay, then this component of velocity being VA cos alpha would have contributed like this. So minus dx by dt would have been VA cos alpha. Okay. On the other hand, suppose only B had been moving and A had been stationary. Then this component of velocity VB cos beta would have contributed to. Okay. So when you superimpose these two, what is happening is that these two components of velocity are contributing to the net approach velocity. This one, this one. Whereas these two components at the moment are not making any difference to x. An instant later, they will start making a difference. But we are not worried about that. We are just thinking at this instant, what is the instantaneous rate at which x is changing? So that is only affected by the components of VA and VB, which are along the x-axis or which are along the line joining them.
No, sir, I didn't
So
get
you
the
can-
part where the y component doesn't matter.
That's what we explained. Okay, let's go back to this one. See, what is happening is, see, in this situation, if we take a general case where a particle is located at some point of time over here at some xy, okay, and it's having some general velocity vector v. So how the position vector of this particle, or you can say the distance of this particle from the origin, how it is changing. Okay, now this velocity vector need not be along this line. It can be some random direction like this. If you consider a general point P here, which has some velocity vector like this and some instantaneous like this. Okay. So what is the definition of V now? It is dx by dt I cap plus dy by dt j cap.
Yes, sir.
What now? Okay. Now at a particular instant earlier, suppose the particle was located over here. Okay, where it had some x coordinate and its y coordinate was 0, and its velocity was still this only. So at that instant, what is the rate at which the distance from the origin is changing? It's dx by dt only, no? So here, see, it is s. Okay, but suppose this was the instant t equal to 0 when the particle started from here. Okay. and this is the general instant t equal to t when the particle is here. So this is the equation. Now in general, at some time t equal to t, the particle is at the position x comma y. So the distance from the origin is root of plus y square. So the separation from the origin, the rate of separation ds by dt is basically d by dt of x square plus y square to the power half. And in that we'll apply this definition. Okay, that this dx by dt is the x component of that velocity and dy by dt is the y component of that velocity. But specifically in that above diagram only, concentrate on what is happening at t equal to 0. The particle is located at the position x comma 0. No? So what is its distance from the origin at that point of time? It is x only. So what is the rate at which it is separating from the origin at that moment? It is dx by dt, and dx by dt by definition is what? It is the x component of that velocity. No? The y component of that velocity, does it contribute to dy by dt? No, no. Understood now?
Sir.
See this red colored vector over here. Okay, this component does not contribute to the x changing. It contributes to how the y coordinate is changing. And this component, the vx component, that is the one that determines what rate at which x is changing. So at that instant, what is the distance from the origin? It's x only, no? So we are not interested in dy by dt at that moment. No? We are only interested in dx by dt because the instantaneous distance is x.
And so we are only interested in the component of the velocity along the direction of the line that joins the 2 points.
Line joining the two. That's why in approach and separation, what we've done from the beginning, the convention we have taken is that the line joining AB, the distance between them only we have written as x instead of s. You can write it as s also, it doesn't matter. So then what we are interested in is how this parameter is changing, how x is changing. What is the rate at which the distance between them is changing? So you can see here that if I break this velocity into two components, the cos component is along this line. So it is dx by dt. The y component is perpendicular to this line. So it does not make any difference to x. Got it now?
Okay,
Is
sir.
it clear?
Yes, sir.
Okay. And now the other case where both of them are moving. So it's just a case of superposition. Okay, that this velocity has a component along towards b of this much, and b has a component towards a of this much. So superimpose those two events. They are happening simultaneously. That a is also moving towards b at this rate, b is also moving towards a at this rate. So we can see that minus dx by dt becomes the sum of these two factors, va cos alpha plus vb cos beta in this case. So we will say that that is the approach velocity of a with respect to b or b with respect to h1 and the same thing.
So had we considered this over some interval of time, then we would have had to consider the y component also, right?
So interval of time, then we'll have to integrate. So what will happen is, like, suppose this is moving in this way. So then what is happening? This is where they are starting from. Okay? But after some time, depending on how much this VA and VB are, what is happening after some time, A might reach here and B might reach here. At that instant, everything will change. No? The distance between them, x, will become this one now. And the velocities also might have changed by then. What we'll have to do now is we will understand that in a general situation, all four of these quantities are instantaneous: VA, VB, alpha, and beta. You understanding the point? Now, all four of them might be changing with time. So to find how the distance between A and B has changed, that is delta x, we have to integrate this whole thing with respect to time.
Okay, sir, I got it.
All right. Okay.
Sir, what if the vectors VA and VB remain the same?
Sorry, what if?
What if the vectors VA and VB remain the same? Will we consider the y component after an instant?
No, because what is happening, the line joining AB may not be parallel to this original line, no? Because they are moving at different rates. You understanding, no? So don't reference it to the x-axis and y-axis. Rather, what you think is x here is the straight line joining AB.
Yes, sir, I
understanding,
got it. Yes, sir.
So a moment later, the line joining AB may not be such that VA is at alpha to it and VB is at beta to it. So even though
Yes,
VA and
sir.
VB vectors might be constant, but alpha and beta will become this thing, instantaneous then.
Yes, sir.
Okay. Now,
Done,
there is
sir.
there is a situation in which, yes, they can be moving like this, such that the approach and separation velocity remains constant. It doesn't matter, it's fine. Okay. Okay, now let's look at an example like this, where what is happening is, suppose I have a two-dimensional motion. Starting from this given position, so both of them have so A and B yes, that's correct, Bhavika. Approach velocity is basically something such that of A with respect to B is the same as approach velocity of B with respect to A, because it's basically equal to what? It is the rate at which the distance between them is changing, is decreasing, where x is distance between A and B.
Okay, sir.
That's one additional thing we can understand. Okay. Now suppose we are taking this special case here in this example where what is happening, A and B start moving from the position shown at time t equal to 0 with uniform velocities. Okay. So suppose x naught is 10 meters, v naught is 2.5 meters per second, and theta is 53 degrees. Okay. Show that their approach velocities remain constant, or let's say the approach velocity remains constant. And find the time at which they collide. So these are not two projectiles, they are just two objects which are moving with uniform velocities in the xy plane. We'll discuss beta, but first do this problem. No? Yes, good, Srijita. That's correct. Anyone else got the answer?
So I sent you in the chat.
I've not received your message, but yeah, Anirudh, I got. Yeah, that's correct. Good. Okay, so the interesting thing you can observe in this question is that because they are going at constant velocity, both of them will be in a straight line path. Okay, and because of the symmetry of that, because both are having same speed and are having symmetrical angles, so at some time t, if A has reached here, then B would have also reached here only. Okay, because the magnitude of A's displacement will be equal to the magnitude of B's displacement, which will both be V naught into T. Okay, and A's displacement will be that V naught T into cos theta I cap plus sin theta j cap, where theta is a constant, remember here. So it will be how much V naught, which is 2.5 T into cos 53, so that is 0.6 I cap plus 0.8 j cap. But B's displacement will just have a negative x component, but of same magnitude, but more importantly, same y component. So minus 0.6 I cap plus 0.8 j cap. So you can see that the y coordinate of A will always be equal to the y coordinate of B, which will be 2.5 into 0.8. So that's how much now? 2.5 into 8 is 20. So 2t. So they will always be such that the line joining them is a horizontal line. This shows you that this will always remain the same. So the approach velocity at this time is also 2v naught cos theta. And at the earlier t equal to 0 also, you can see that the approach velocity was 2v naught cos theta. So this shows us that it remains the same. The approach velocity that is 3 meters per second is uniform with respect to time. Okay. And now we can see that therefore, if the distance between A and B is x, then minus dx by dt is equal to v approach, which in this case is constant. Okay. So once it is constant, we can say that delta x is 3 delta t. So if they collide at a time, let's say capital T, delta x will be 0 minus the initial distance between them, which was how much now? Ten meters. Okay. So suppose continuing further like this, they collide at some time capital T. So from 0 to capital T, you can see that the distance between them has changed by a factor of minus 10, but it's changed at the rate of minus 3. So the time so we're using this. So you can see that the time of collision It's 10/3 as you have rightly calculated. Okay.
Done, sir.
Done, sir.
Yeah. Okay, so now another interesting example where you can understand about, get some more insight about approach and separation velocity is the case we were talking about a little while back, that suppose I have two objects moving on a circular path, okay, both at uniform speed. A is here at some time and B is here. Suppose they are subtending an angle theta. So this is the situation at t equal to 0. So if A and B are both in what is called uniform circular motion, yes, so we'll be studying about this in detail in just some time later. So this is circular motion at uniform speed. Such that VA is equal to VB, equal to, let us say, 2 meters per second, and theta is equal to pi/3 at t equal to 0. Find their approach or separation velocity at t equal to 0. And secondly, if the radius is equal to 4/pi meters, then find their approach or separation velocity at t equal to 2 seconds. Okay, and finally show that equal to 0. Okay. So first, just try to visualize this problem geometrically. You have two particles which are moving in a circular path like this at the same speed, and both are moving at uniform speed. Okay. So just try to visualize if they're moving at uniform speed, what it means about them. Okay. And once you've done that, then systematically calculate each of the three parts that I've given you, and you'll realize how what you've realized in the first thing by understanding their motion just from geometrical visualization, how that is justified by the concept of approach and separation velocity.
Done, sir.
Yeah, students, back online. Okay, so some technical problem at my end. Anyway, so let's continue with this. So I hope all of you understood what's happening here. So you'll see that, for example, at t equal to 0, if this theta is 60 degrees, okay, so you'll also realize that this is becoming an equilateral triangle because this side is equal to this side. So this angle is equal to this angle. Okay, so it becomes 60 degrees. Okay, so that means that these are 30 degrees. Okay, these angles here are 30 degrees, right? So at t equal to 0, you can see that the separation or approach velocity. So suppose we write it as an approach velocity, then it should be VA cos 30 minus VB cos 30. You understood why it's minus now? Because I've written this as an approach. So VB cos 30 is actually contributing to a separation velocity. So for example, suppose VA had been greater than VB, then they would have had an approach velocity. But suppose VB had been greater than VA, then they would have had a separation velocity. But in this case, what is happening? VA has the same magnitude as VB. Okay, so that means what's happening, that the approach velocity is becoming 0.
Yes, sir.
Okay.
Yes.
Now the fact that they are moving at constant speed. Now you can also see that we are specifically talking about the time of 2 seconds. So in 2 seconds, what is the distance they would have moved? The distance moved by A. This is not displacement. This is distance now I'm talking about. Okay. So the distance moved by A is equal to the distance moved by B, which is equal to that common speed into time. So that would be over here. How much it would be equal to 4 meters. Okay. And if you see the what is the circumference 2 pi r, it is 8 meters. So that means where they've reached the positions which are diametrically opposite. So at t equal to 2 seconds, B is over here and A is over here. They've covered an angular displacement, what we call. We'll talk about all these things in more detail in circular motion later. So each of them has covered an angular displacement of this. Okay. So the distance they have covered, this distance is half a circumference. Okay, so they are here. And at this moment also the situation is same. This VA is equal to VB. I mean, obviously it's the same, you can understand. Okay. And this angle equal to this angle, 30 degrees. So even now this B approach or separation, whichever we take, is equal to 0. Okay, so Bhavik, I'll explain this thing once again. Okay. So see, we'll come back to this diagram, but in general, suppose I have two particles which are right now located something like this. Okay, this is the line joining them. Now suppose this one has a velocity like this at an angle beta. So what is happening as a result of this? They are having a separation velocity of BB cos beta, or you can say that they are having an approach velocity of minus VB cos beta. No? But now along with that, suppose this is having a velocity like this. Suppose this is having a velocity VA like this at an angle alpha. So now in this case, what will happen? The approach velocity will be the superposition of this event and this event. No? So it will be VA cos alpha. But because of this event, there's a contribution of minus VB cos. Okay, so this is the net approach velocity. Or you can say that the separation velocity is VB cos beta minus VA cos alpha. Now, suppose this quantity is larger than this, then this will be separation will be negative and approach will be positive. That means actually what's happening, they are approaching each other. And vice versa, if the other way around, right? Is this
Yes,
clear,
sir.
Bhavika?
Yes, sir.
So now go back to that diagram and we'll see that that same concept only we are applying over there. But what is happening that the two angles are same and the two speeds are also the same. So the net approach or separation velocity, whatever you call it, that becomes 0. At t equal to 0, at t equal to 2 seconds also is the same situation. And at any general time we'll see is the same situation. So if you see any general time, suppose at time t, A has reached here at some time t. And it might be that it's done many rounds of this and come here. It not be that it's directly gone from here to here. So B will obviously be here only, because they would have
Sir.
covered the same amount of distance along the circles, and this would remain the same. So at any time t, the approach or separation velocity would be 0, because what would happen is that the components of velocity along the line joining the two of them, that is the chord AB, would be exactly equal. So they cancel each other. Yes, somebody had a doubt? Okay. Okay. Now while this question is complete on its own, now you can also imagine that suppose A's speed was more than B's, instead of both the speeds being the same, then this whole scenario would have changed. Then they would have some positive approach velocity, and as the two of them are moving, that chord length would decrease, the whole angle would change. So from instant to instant, your approach velocity would be increasing with time, and eventually A would collide with B.
Yes, sir.
So that situation might be more complicated. So we won't get into it as a numerical problem right now, but you can understand from this that if the speeds are same, the distance between them remains constant, because that chord AB is like a fixed chord which is just moving. It's a chord of fixed length which is just moving. So you can see its justification from approach and separation velocity concept. But you can also understand the counter to that argument, that if VA and VB had not been the same, then it would not be a fixed chord length. Okay, that chord length would either be increasing or decreasing depending on whether they're having approach or separation velocity.
Yes, sir.
Okay. Now next we will see the application of approach and separation velocity in constraint relation problems. Okay, these are not kinematics problems per se. They can be thought of as part of kinematics, but they're not in that sense kinematics problems. They are constraint relation problems. But how we can make use of approach and separation velocity. So constraint relations become part of solving of physics problems in various situations, whether that is Newton's laws of motion, or later you will see work by energy, or in class 12th you will see it might be part of electromagnetism. But many a time when we are solving a physics problem, we are required to solve some constraint relation because of some kind of constraint that is coming within the problem. Okay, so let's see how we can make use of approach and separation velocity in certain situations. So first example I'll take is an example which we had seen long ago in calculus. We had solved, but using calculus concepts, rate of change concepts. Now we will use approach and separation velocity concepts. So suppose this is a wall which is perfectly vertical and a floor like this. Okay, and now what we have done is we have taken a rod, placed it somewhere over here. Okay, such that this rod is, so this is a rigid rod of length L. Now this is slipping such that at the given instant of time, this point B has a speed dv, this angle is theta, and this point A has a downward slipping speed of B. Now if at a certain instant of time, the speed of the point B is, let's say, 2 centimeters per second, and theta is equal to 53 degrees, then want to find the speed at which the point A is slipping downwards at the same instant. What is the speed at which A is falling? Okay. Now, previously we had seen that we had used a calculus method that, the length, if you take this distance as X and you take this distance as Y, then we have the constraint relation. So calculus method of this was that the length of the rod is a constant. That means the rate of change of square root of x square plus y square should be 0. Or if the rate of change of square root of something is 0, that means the rate of change of that quantity itself is 0. And dx by dt was plus vb and dy by dt was minus va. Okay, so this method we've seen before, but now we will use the approach and separation velocity method. So anybody can give me a hint how we can use the same concept that the length is constant, but use that concept in terms of approach and separation velocity.
So we'll take component
So
of VA along the
superposition.
rod, VB along the rod, and
Yeah, so
separation velocity should be 0.
Yes, sir.
very good. Okay. So even before we start that, what we can say is that if the length L is constant because the rod is rigid, what we can say about these 2 points A and B? They are at fixed distance.
Yes, sir.
L is constant means what? That the approach or separation velocity between A and B should be how much?
0.
Should be 0. Correct. Okay. So what is happening here is that the distance between A and B is equal to L, which is constant. Unless the rod breaks or stretches or something like that, which is not happening over here, this cannot change. So this implies that the approach or separation velocity, whichever we consider, of A with respect to B or B with respect to A, whatever, this must be 0. So this is our constraint relation now. This is effectively what has become a constraint relation, because it has come from the condition of the question that L is fixed. So this is the constraint relation that is coming from the system constraint, that the rod is rigid, so its length is constant. And once you have expressed this, now you can see life is very simple, because you know how to apply the concept of approach and separation velocity geometrically. You can see that this angle is theta and this angle is 90 minus theta. So directly, if I want to write the approach velocity, you can express it as what? You can express the approach velocity, for example, as VA cos 90 minus theta minus VB cos theta. Or you can express the separation velocity if you want as just the reverse of this. It is VB cos theta minus VA cos 90 degrees or pi by 2 minus theta. So now just substitute this. So this quantity should be 0. So that implies that VA, which is unknown, cos 37 minus VB, which is 2 centimeters per second, into cos 53 degrees, that should be 0. That's it. That's become our single equation. So no chain rule, differentiation, all this thing is not, that's done now. So VA we can see is 2 centimeters per second into 3 by cos 53 is 3 by 5 and cos 37 is 4 by 5. Yeah, so 3 by 5.
So we've been taught this actually. We've been using this method only till now to solve problems.
Yeah, very good. Okay. So now you can see this can be used in more complex situations also, where you have multiple pulleys and things like that also.
So can you give an example of that multiple, please?
Yes, we'll come to that only next. Okay. So first of all, like, just go through this once carefully, all of you. Anybody has a doubt in any part, especially the conceptual part, please let me know. Okay. Okay. Now let's look at another example. we have some kind of a surface here. So if this is moving horizontally at VA and this is moving vertically at VB, okay. So if VB and theta are known at some instant of time, then calculate PA in terms of PB and theta at that instant. Of time t. So here what we can do is that, let's say this point where the thread is attached to A, I'm labeling that as A again, and this point where the pulley is there, I'm labeling that as P1, let's say, or P, let's say, okay, and this is B. So the total thread length, so if I label the distance AP as Z, and this one as Y1 and this one as Y2, is equal to Z plus Y1 plus Y2 plus a certain amount of thread which is going around the pulleys and all that. So I'll just label that as some, say, small n. So this is the total thread length. So this small l is the part of thread in contact with the two pulleys. You can see that that's not going to be changing very much. Okay. So this thread length remains constant. This total thread length remains constant. So that means dz by dt plus the rate of change of y1 plus y2 should be 0. Now you can see that dz by dt is such that minus of dz by dt is equal to the approach velocity of the point A towards the pulley P. Does this make sense to all of you?
Yes, sir.
Yes, sir.
Okay, and whereas dy1 by dt is positive of the separation velocity of the block B from the pulley, and same with dy2 by dt.
Yes, sir.
So this statement now basically means what? That approach velocity of A towards the point P should become equal to double of the separation velocity of B from the point P. Okay. Or in other words, the rate at which the Z part is decreasing should be double of the rate at which Y1 is increasing or Y2 is increasing. Or it should be, so basically it's this, that minus dz by dt, the rate at which Z is decreasing, should be the sum of the rate at which Y1 and Y2 is increasing. So this is only your 2 times V separation. and this is only your V approach. So यहाँ से thread length जितना decrease हो रहा है for Z, Y1 and Y2 उतने से increase हो जा रहा है cumulatively. So that is the whole concept here. Got it now? So you can see now this is very simple. What is the approach velocity of A towards P? Now A is a point that is moving like this. This is VA, and P is a fixed point over here. And at the given instant, the angle between the velocity and this line is theta. So this approach velocity is becoming VA cos theta. And this should be equal to twice of. So that is your constraint relation now, that VA is equal to 2VB sec theta, correct? I'm sure all of you know the alternate method, how you would do this by calculus. You would have to define this distance between A and P as a hypotenuse. Take this distance as x. This is a fixed distance h. So z square would be equal to x square plus h square. Then you differentiate this. Like this. So dz by dt, the rate at which that thread length is changing, would be equal to x by z, which is cos theta times dx by dt. So you can see that dz by dt would become minus va cos theta, because dx by dt would be minus va.
Yes,
And
sir.
then you would see on the other side. So that kind of method. Okay. But you can see all this lengthy calculation can be avoided by just using this. So please go through this example very carefully, people. If there's any doubt in any of the steps, let me know. Okay. Because while this is a very nice shortcut method, but it's also easy to make mistakes in this. Okay. So be careful about each and every step. I mean, see, it's easy to make mistakes even in the calculus method. You have to be careful there also. So definitely, like, this is a more advantageous method because it's saving you time, but it's just that be careful. Okay. Right, now let's look at another situation. Again, this is the type of question you would have seen many a time. Okay, now suppose what is happening here is that both these ends of these threads are being pulled down by some external agent at the same speed, V0 and V0. And this whole arrangement is made in such a way that this is symmetrical. So this angle is equal on both the sides. So this angle is instantaneous, of course. And as a result of that, this block is going up with some velocity. So given the value of V0 and theta at some instant t, you want to find V at that same instant t. Okay, so again, in this, we can make use of this concept. You can treat this point, let's say like a moving point P, and you can treat this point P1 or let's say this point P2 as two fixed points. Now this moving point is moving up at V, and let's say this point A or this point A2 is moving down. So you can see that the total thread length is conserved. So if these two are Y and Y and these two are Z and Z, so the total thread length, which is plus 2Z, that, sorry, not X, Y plus Z should be 0. Okay. So now you can see that dy by dt is actually a positive quantity, and that is equal to the separation velocity of the point A1 or A2 with respect to P1 or P2. And that is equal to my B. Whereas dz by dt is a negative quantity, it is decreasing at the rate of approach velocity of the point P towards P1 or the point P towards P2. They are symmetrical, and that is equal to how much in this diagram? It is becoming V cos 90 minus theta. Because this angle here, 90 minus theta, same as this angle. So that's it now. The problem is done. So when you substitute here, you can see that dy by dt should be minus of dz by dt. So V0 should be equal to V sine theta. So that's it. Your constraint relation is completed. Okay, people. So hope this example is also clear to all of you.
Yes, sir.
Yes, sir.
Okay, very good. So these are some situations in which you can use constraint relations like this. Why is the population diminishing? You people don't have anything in the afternoon, right? No lecture or anything.
No, sir.
No, sir.
Okay. So I just want to continue till about 12:30. A little bit half an hour extra time kind of thing, because we need some additional time to discuss this whole thing in one sitting without breaking it into two lectures.
Sir, even if the thread length on both sides between P2 and A2 and P1 and A1 hadn't been equal, we would have got the same constraint relation, right?
Still got the same constraint relation, so long as it is symmetrical. That is, the two thetas are the same and the two V0s are the same on the two sides.
Yes, sir.
Okay, now this thing can become quite a bit more complicated if we were pulling the points A1 and A2 at different speeds, because then what would happen, that block P would not have a vertical motion anymore. Understood the point? No? Suppose
Yes, sir.
the point on the right hand side A1 was being pulled at a faster speed compared to the point A2, then what you would see that this side's thread length would be decreasing at a faster rate than that side. So then the block P would have a horizontal component of velocity towards the right, and a vertical component of velocity upwards. And the constraint relation would become that much more complicated, whether you do by calculus or by approach and separation velocity method. But even then, approach and separation velocity method would be the easier way of solving it. Okay. So I'll
But it's
just.
fully attached, no?
But the
Even
pulley
if
is
you
attached
pull
to
up
P.
in the same.
The pulley is attached to P. It's not like the pulley is on a channel. You understanding this, no? The pulley is attached to the block P, no?
Yes, sir, but the pulley will always move up in such a way, right, that its relative velocity to both the pulleys is the same.
Why it has to be that way?
So that's the
That's what I'm saying,
constraint of the
right?
movement pulley, right?
Now why it is the same? Because the V naught on the two sides. Okay, let's discuss this with an example. Okay, make it clear. So suppose now we have slightly different situation compared to that diagram. We have between a ceiling and a wall. Actually, wall doesn't matter over here. It's just suppose we have this situation. See if I make this a little bit easier. Okay. Okay. Now, if this is going down at a speed V1 and this is going down at a speed V2, so find the relation between V1, V2, and theta.
So 2v2 cos theta is equal to v1.
2V2
Cos theta
cos
is equal to v1.
equal to V1. Yes, very good. That's correct.
And so the pulley is moving up
Yeah,
in
in
a
this
straight
case
line
also,
only.
it will always move vertically. Okay, in this situation also.
Sir,
Move
if there
vertically.
hadn't been a pulley, if we had straight away attached the block to the pulleys, then so the block would have
Yes, that would be the
acted
situation here. Correct. So instead of this pulley here, if this was fixed to the ceiling here, okay, then there is that situation where you're pulling this down. This has a different kind of path. Okay, then what this does is a little bit more complicated. So we'll come to that also.
Yes, sir.
So anyway, in this diagram also, if these two are Z and this is Y, you can see that the rate of change of 2 times the rate of change of Z plus the rate of change of Y should be 0 when you conserve the thread length. Okay, so 2 times the approach velocity of A towards either P1 or P2, where P1 and P2 are these two pulleys. That should be equal to the separation velocity of B from P2. Just note this down, people. I'm just coming. So 2 times B2 cos theta in this case. Yes. This point is going up at B2. So its approach velocity towards P1 or its approach velocity towards P2 at any instant is the same. So that should be equal to this separation velocity, which is V1. Okay, now an interesting second version, or rather actually different version. This thread is directly attached. And then there is another thread attached to this side. That is going around a pulley. This we are pulling at a speed v. So at some instant of time, when this angle is alpha and this angle is beta, realize that this has some velocity. So I will not give you the hint of the direction. So find PA in terms of alpha, beta, and beta. Actually, to understand this question, fully better, you can draw a diagram where it doesn't appear to be so symmetric like in that diagram, because it need not be symmetric. So let me try and illustrate that. More like this. So let's even make a numerical problem out of this. Okay, let's say at some instant, alpha is equal to, let us say, 37 degrees, and beta is equal to 45 degrees, and B naught is equal to, let's say, 1.2 centimeters per second. So find the velocity of the block. So you have to also indicate the direction as well as the magnitude. You want to try this or you want me to give you a hint?
No, sir. Let
So
us
we'll
start.
try.
We'll try.
Try. Good. Okay, so can anybody tell me how to determine the direction of the block's motion? Or see, as you're pulling this end of the string down, what kind of path will the block be taking?
Diagonal.
Sir, it would have a horizontal component towards right.
It will have horizontal also and vertical also, but is there anything specific
Yes.
about its path? See, there are two threads now, both the lengths are conserved, but this one is very interesting. This length is conserved, means what is happening? The distance of the point A with respect to, let's say, this point O is constant, na?
It will have a circular
Yes,
path.
sir.
Yes, very good. So the most important thing here to understand is that the path of this block will be a circular path like this with respect to this. So at any point of time, this distance L is remaining constant. So if it's having a circular path, what about its velocity? It is tangential. So in this diagram, the one which is little bit easier to understand, the velocity of the block B at this instant, let's write that as the V vector, that has to be at 90 degrees to this.
Yes, sir.
So the block A is describing a circular path. With respect to the point O, okay, because L is fixed in length. So V velocity is perpendicular to the line OA. So two ways of understanding that circular motion where the velocity is tangential. Another way to understand that because L is fixed, the approach or separation velocity of A towards O should be 0. That means the V must be perpendicular. That is why. So once you got that, now rest is simple. Just conserve the other thread length. So you'll see that if this pulley is P and this point is, let's say, B, you'll get that the approach velocity of the point A towards the pulley P must be balanced by the separation velocity of the point B from the point P. This is the second string's conservation. So now it's just a matter of working out the angles and all that. Okay, that also you can do quite simply because alpha and beta's numerical values I've given you. So you just take that. You just have to use trigonometry identity and all that.
So we're done.
Right. So can you send me the answer?
Sir, V sin alpha plus beta is equal to V naught.
Alpha plus beta कैसे हो गया बेटा?
Sir, क्योंकि theta with the
This angle is alpha, no? Right? Is correct?
yes sir,
So this angle is how much?
90 minus
90
alpha
minus
plus
alpha plus beta. Yes. So your answer is correct. Okay. So what we'll see that when you write this, yes, very good, Abhinav. That's correct. Okay. So the approach velocity of A towards P will become V cos of 90 minus alpha plus beta. So that's correct. That will become sine of alpha plus beta. Okay. Should be equal to this separation velocity. So V sine alpha plus beta should be equal to V naught. So in this particular case, it is sine of 37 plus 45. Okay. So you can write that as sine 37 cos 45 plus cos 37 sine 45. So this will become how much? V will become 5 root 2 by 7. Is that correct? If not. Yes, Rijita, you have a doubt, beta?
Yes, sir. So basically we are equating the y components.
Y component? No, beta, we are not equating the Y components. Okay.
Sir, I had
I'll tell you
taken
why.
90
Because see,
minus alpha plus beta and I got it wrong.
nahi. So see, what is happening now? Observe this line AP. This line
Yes, sir.
AP, that is the line along which the thread is present. No? So we want the
Yes,
approach
sir.
velocity, okay, of A towards the point P. Now compared to this line AP, the velocity of the point is actually lying like this. It's a vector like this, you know. So this
Yes,
angle
sir.
becomes important. No? This angle, let's say this angle is some theta. So the approach velocity becomes how much? It becomes V cos theta. Okay. Now the main thing is we have to find out this theta. Now how to find out this theta? So this is the
Yes,
thread
sir. I
on the.
got that theta. Yes, sir.
Got it now? Okay. So this
Yes,
angle
sir.
is 90. You can see that the angle with the vertical. This one is alpha. So this one is alpha. Okay. And this thread itself is at an angle of beta. Okay. So that's how we were getting that this theta is equal to 90 minus of alpha plus beta. Okay.
And sir, that is equal to V naught sine beta.
So no, sine of alpha plus beta.
No, sir. Sir, the other part, right hand side.
No, that's direct. Na? See, this is falling vertically. Na? So
Yes, sir.
the pulley is here and this is falling vertically. Na? So the separation
Yes,
velocity
sir.
of the point P from P, that is directly V naught. Because here there's no angle involved. Na? It's moving along that line PB only. Na?
Sir, but we have to take it along AP.
We have to take it along the thread. Na, beta? See, the thread is vertical over here. Na?
Yes, sir.
You understanding? Na? So if this thread length is Y over here, what is the rate of change of Y? It is plus V naught. Na? So that only is the separation velocity. Na?
Yes, sir.
Got it?
Yes, sir.
No. So basically the
Yes, sir. I got
component of
this.
the component of A's velocity towards the point P should be balanced by the velocity of B, which is directly away from the point P. So that's why on the other
Yes,
side of
sir.
the equation. Okay. And then it's just a matter of calculation. Okay, working this out. So Abhinav, this was the answer you got, no? Of course, substituting the value of V naught as 1.2, I think it was centimeters per second or whatever. Oh no, I had not given the value. Yeah, I had given the value. Yeah, 1.2 centimeters per second. So you substitute that. Okay. Okay, now next we will look at a very specific type of problem in kinematics, which will be solved using this approach and separation velocity concept. Okay. So this is a very classic problem which was asked in Olympiads long time back as a subjective question. So we'll find it in all the reference books. So A, B, and C are three particles which are located at the corners of an equilateral triangle initially at time t equal to 0. And what happens is that they are chasing each other at a constant speed of v0. So chasing each other means that the direction of A's velocity is always pointed towards B. The direction of B's velocity is always pointed towards C, and C's is always pointed towards A. So their velocity vectors are always, they like sense where the other particle is, and they point their velocity vectors towards the other one at a magnitude of v0. So if this is the situation at time t equal to 0, A, B, and C are moving in a two-dimensional plane at constant speeds v0, such that A's velocity always points to B. Similarly, B's velocity always points to C, and C's velocity vector always points starting from the position shown at t equal to 0. Not exactly circular tracks, but yes, curved kind of paths, and yes, they will collide at the centroid simultaneously. So first of all, we have to show that all three will converge at the centroid of the triangle simultaneously. And we have to find the time taken for them to converge. So let's not be in a hurry about like how to calculate this time. Let's try to visualize the problem first. Okay, so this is what I suggest you do, that from the starting diagram, just try to understand that at a very small time dt later, how the particles will look, like where they are placed and how their velocity vectors are pointing. And then trace it another time dt later. And from that, try to understand the pattern that after a certain amount of time, how you think A, B, and C should be placed, where they should be, what kind of path they moved along, and how their velocity vectors are. So start with the diagram that is given and try to trace their path first at a time dt later, then again another time dt later. So that will give you some idea. And from that, you try to understand that instead of dt at a fair amount of time t later, not a very small amount of time dt, but a fairly large amount of time t later, but they have not yet collided. Okay, so at a reasonably large amount of time before they collide, where they would be, from those first two instances of dt, you try to trace out how they would have moved in a time t and where they would be located. So that will give you some idea about the geometry of the problem. And then you start thinking about how you can use approach and separation velocity concept.
Sir, done.
Okay, people. So I'm just going to get started with the geometrical understanding. Okay. If you've already done that, then just continue working on it. Okay. So if the particles have started from this kind of a situation at t equal to 0, now first of all, I'll imagine what's happening just at a very, very small time later. Okay. So at some time dt, let's say this particle A has reached here, B has reached here. Because instantaneous velocity, hardly it's changed its direction. So it's more or less moved along that straight line only. So at time dt, C is now here, B is now here, and A is now here. So what will happen? Immediately the direction of the velocities will change because this thing has changed now. Their mutual orientation has changed. It has become like this now. So immediately the direction of the velocities will change by a small amount d theta. But you'll see interestingly, the geometry of them with respect to each other is the same. they're still forming an equilateral triangle. So that is the interesting thing. So while the velocities have changed in direction, okay, the angles would have remained the same. So now this one's velocity is in this direction. This one's velocity has turned slightly. It has become in this direction. This one's velocity has turned slightly. It has become in this sort of direction. But still, earlier also the angle that the velocity vectors were making, this was 60 degrees. This was 60 degrees. And this was 60 degrees. Now at the new instant, the triangle has changed, so the angle has remained 60 degrees. So a little while later, let's say they've reached here, here, and here. So now they're forming a new triangle like this. But still the mutual relationship between the velocity vectors is the same. So, basically what is happening is they are forming a diminishing sort of triangle. So you realize that the individual paths will be like this, some kind of curved path like this till it reaches the centroid. But at any other instant t in between also, they'll be forming a triangle like this, an equilateral triangle. So at that point of time, the distance between them is r. And again, the velocities will be having that same mutual geometry. So at any point of time, the approach velocity of A towards B, or B towards C, or C towards A is having the same relationship. It is V0 plus V0 cos 60. It is 3 V0 by 2. So this approach velocity is a uniform approach velocity. So the individual motion with respect to ground frame is very complex. Okay, but the motion of A with respect to B, or B with respect to C, or C with respect to A is always very simple. That they are moving such that one of them is moving directly towards the other, and the other is moving at 60 degrees with respect to the line joining them, like that. Okay, so this makes sense, people?
Yes, sir.
Yes, sir.
Yes, sir.
So now how I can make use of this fact to find that. So then first part you can see that at any time they are forming an equilateral triangle, and with time that equilateral triangle is diminishing. So that itself shows you that they will converge at the centroid, let's say G. Okay, so therefore, they converge at the centroid, because at any time T, they are forming an equilateral triangle with the same centroid as the original one. Same centroid and decreasing side length R. Okay, so that therefore they must think at the center. So now another interesting thing you can see here, apart from this fact, is that at any time t, if you look at the orientation of any of the particles with respect to the final destination, which is the centroid, even that is a fixed relationship. because this will always be at an angle of 30 degrees with respect to this. So the approach velocity of A towards the centroid, or B towards the centroid, or C towards the centroid, that is also a fixed quantity. It is V naught cos 30 degrees, or root 3 by 2 V naught. So that's another interesting observation we can make, that okay, this is also uniform. So now we can make use of either of these two facts, this fact or this fact. So at time capital T, suppose they collide at the centroid, then you can see in that time interval from 0 to capital T, the distance between A and the centroid, or B and the centroid, or C and the centroid should have changed by how much? The original distance, which is L by root 3. Okay. Or the distance between A and B, or the distance between B and C, that should have changed by an amount of L. So delta S between AB, the relative distance traveled of A with respect to B, is minus L, like that. So we can make use of either of these. So if they collide at the centroid at capital T, then we can see that the fact that approach velocity of A towards B is equal to 3 V naught by 2. So this should be equal to minus of delta x between AB, that is the distance between AB with respect to time, because this is uniform. Okay. So this will become minus L, okay, or delta x between A and G for that matter will become minus L by root 3. Now this also I'll show you why it's L by root 3. But first let's look at this. So this is minus of minus L by T. So you can see 3 V naught by 2 should become L by T. So the time should become 2L by 3 V naught. So whatever we are doing between A and B, we can also do between B and C, or C and E, one and the same thing. So that is one thing we can make use of. That is this fact. We are making use of it here. But we can also make use of this fact. Now for this fact, you have to understand that when we draw an equilateral triangle, you should know that altitudes cut in the ratio of 2:1 at the centroid. This is a fact that you know, people.
Yes, sir.
Yes, sir.
Yes.
2:1 ratio hota hai na? So the distance AG, for example, will be equal to the distance BG or CG, and that will be 2/3 of the altitude. Okay. And the altitude, if the side length is L, will be L root 3 by 2. So that's how we get this as L by root 3. So now make use of this. Okay. So making use of this fact here, B approach of A towards G is root 3 by 2 V naught. So that should be minus of delta x between A and G divided by the time. That is L by root 3 divided by the time. So again, you can see that root 3 by 2 V naught should be equal to L by root 3 upon time. So you will get the same relation, that time is equal to 2L by 3 V naught. This is another way to visualize that each of the particles is moving in a very complex kind of way, but such that its component of velocity towards the centroid is always remaining fixed. It's remaining V naught by root 3. Root 3 by 2 V naught. Okay. So the time at which it reaches the centroid will be the initial distance it had from the centroid divided by that velocity. So that is L by root 3 divided by this. Yes, Janvi, you have a question, beta?
So if the question had been find all the instants of time where the triangle formed by the instantaneous positions of A, B, and C is of the same orientation as the original triangle, then how would we have solved it?
Then you have to solve the trajectory in ground frame individually of that. Okay, so that is considerably more complex. Okay? So just right now we will not worry about that. Okay, the question here specifically is just this much only. Okay,
So when will
Yeah.
we worry about that?
I mean, it's a more complex
After
problem
chapter
mathematically, so maybe not at JEE, not at JEE level. Okay. Yeah, somebody else has some doubts. I'm seeing hands raised, but unfortunately, I'm not able to see who. So,
So Srijita.
yeah, Srijita, beta, go ahead.
Sir, how do we solve it in ground frame? I tried, but I couldn't get it.
Yeah, that is the thing. In ground frame, the motion is much more complex. So, the level of match that we know right now, we cannot solve it directly in ground frame.
Yes, sir.
Okay,
Sir, and
understand?
what if this triangle were not equilateral and scalene or any other type of isosceles?
So again, it becomes much more complex. So in that case, right. So or even if it was equilateral, but if the speeds were not same, if all three were not moving at v naught, then they would not, they might not collide only simultaneously. You're understanding the point, no?
Yes, sir.
So without that symmetry, this problem becomes impossible to solve by this method of approach and separation velocity. Okay. So I mean, whether or not it is solvable at the end of the day is a question in itself. Okay. But the point here for us is that we are looking at applications of approach and separation velocity. So in any case, that type of problem cannot be solved by using approach and separation velocity. So it goes outside the scope of our kinematics over here. Understanding the point, beta?
Yes, sir.
The kinematics on its own is a much wider subject than JEE level kinematics. You can study it at different levels of physics later also. So ultimately what happens is if it is not solvable by maths, then we have to do simulation. Now we have to write a computer program which will actually track the path nanosecond by nanosecond or microsecond by microsecond, depending on what kind of accuracy you want. And from that we have to trace the path. Okay.
Yes, sir.
So many real life problems may not be solvable in that sense by using pen and paper mathematics. We might require to do simulation or something. And like in real life, what happens that even sometimes the simulation cannot be that accurate because, suppose you have missiles which are fired like this on each other, but there are other factors like wind, then there is drag forces, then the missiles might be leaking some fuel. So because of that, the trajectory might be changing. So there might be a single problem might have hundreds of variables. Like we are doing problems which are one or two variables at a time. So, even doing the simulation and writing the program for that might be something that takes months. And at the end of the day, it might not agree with real life situations. So real life engineering and technology problems are much, much more complex. Okay. So, but again, the thing is, see, you have to learn at JEE level, what is the thing? Our main thing is we have to learn the approach to problem solving by analytical means and by using the principles of physics, chemistry, and maths. So right now we limit ourselves to problems that we can solve by using pen and paper mathematics, because that is the fundamental way of solving problems that we have to learn. And then later when we go into engineering, technology, or applied science, then we get into those situations where you use simulation. It might take you days or even a month if you're in a, if you're writing a project which is ultimately solving a real life problem which you will be publishing in a, proper science paper or official publication. Then it's not uncommon that, the whole process takes literally months to complete that.
Yes,
Okay.
sir.
So I think my answer has gone a little bit beyond the scope of your question itself, but I'm just giving you an idea that not everything is solvable on pen and paper for that reason. Okay. So that part comes later. Here we will concentrate on those type of things which are solvable for us using the methods that we are learning. So we will, in this case, the triangle problem like this, we will always solve for the symmetrical case, where the triangle is also symmetrical and the motion is also happening uniformly for all three.
Yes, sir.
Okay, so people, that's it for today's session. Thanks for being patient and exceeding the time so much. So with this, we complete all the concepts of kinematics. Okay, maybe we will do a few more questions in the next lecture also, before we proceed ahead with circular motion. And when we start with circular motion in the next lecture, you'll see the first part is again kinematics only, but it's kinematics of circular motion. So we'll be discussing the equations of motion for particles which are specifically in circular motion. And then from there, we'll be moving on to more things like centripetal force and all that. So dynamics will come into the picture. Okay. So that's it for today, people. I will send you some revision questions also to do. And in the meantime, do kinematics 2 from your booklet 1. Okay. Yes, kinematics 2 has to be done completely now. Kinematics 2 beta has more to do with these kind of concepts, relative velocity, velocity of approach and separation and all these things.
Okay, sir.
Sir,
So in that sense, Kinematics 2 is like the JEE advanced level applications of relative motion. Yes, beta.
sir, in Resnick Halliday, there is a version of green cover page, blue, ochre, and red. Which one is to be
So
bought?
actually, you see that there are different authors you will see, na, where the third author is always different. It is either Amit Gupta or it is somebody else, and the publication is also different. What I prefer is you get the red colored one, which is Resnick Halliday and Crane. Okay.
Yes, sir.
Because you are not doing the book Resnick Halliday for doing JEE level questions. You are doing it for doing the theory part, which is like best from the international edition. For JEE level questions, you are doing questions from the module from H.C. Verma and from D.C. Pandey. Okay. So best is to use Resnick Halliday for theory reading only. So that is why I don't want you to do the editions which are by Amit Gupta, etc. Because what they have done is they've added JEE level problems, but the theory part is the same. So no need to go for them.
Yes, sir. Thank you, sir.
Okay, people, all the best. That's it for today.
But I've already got the Amit Gupta Blue edition, so what to do?
It's fine. I mean, it doesn't make that much difference. It's just that the red one has few more examples in the theory part, and the theory is a little bit more descriptive. But if you already bought it, it's really doesn't make a huge difference. It's like just a 2% difference in the theory part. So just go ahead. But again, use that book only for reading theory. Don't get into the problems of that, because unnecessarily you'll be trying to solve too many problems in physics and then compromising on maths and chemistry. Okay.
Okay, sir.
Thank you,
Thank
sir.
Thank you, sir.
Thank you, sir. Bye.
Thank you, sir. Bye, sir.
Okay.
Yes, sir.
Bye.